Okay, a couple more quick examples here using geometry. I'm going to try to avoid using the limit of a Riemann sum as much as possible. I may have to, for some examples, you may have to apply some properties, do a little geometry here and there, and then do a limit of a Riemann sum for just like a small part of it. But if you can narrow it down to a small part, that makes the limit of the Riemann sum a lot easier to do. Although, I'm saying that right now, but actually, both of these examples, I think we could do both of these without having to do any limits, just using some geometry reasoning. So this first one, let's think about the function y equals the square root of 4 minus x squared. That is one of those semicircles. Rearrange that, you'll get x squared plus y squared equals 4. So we're talking here about a semicircle of radius 2. Okay, we know it's the top semicircle because it's the positive square root. So now this is the integral from 0 to 2. So we're talking about this, just this quadrant of the circle of radius 2 centered at the origin. Okay, so the net area there, since it's above the x-axis, it is positive, but that net area is going to be 1/4 of the total area of a circle of radius 2, which is going to be pi r squared, or pi times 2 squared. So we're going to have a 4 in the denominator. We're going to have a 4 in the numerator from the 2 squared here. So those will cancel out, and this is just equal to pi. This integral equals pi. So that was pretty easy. So there's that one. And the second one here, x cubed. I didn't tell you anything about x cubed. Let me pull back that. Where was it? Let's see. These were the three basic integrals using geometry that I explained. One was x, so one of them was 1, one of them was x, and one of them was the circle, right? The circle formula here, equation. So what's up with this x cubed? Well, all right, just hang on a cotton-picking moment, as they say. My dad used to say that. Still does. Here's what x cubed looks like, right? Y equals x cubed. Let's say -1 is like here. Oops, -1. Let's say 1 would be over here then. Let me draw this out for a second here. All right, there we go. So we'd be talking about this region plus this region. It's always between the curve and the x-axis. This is a negative region over here, right? And this is a positive region because we're below the x-axis is negative and above the x-axis is positive. And y equals x cubed has symmetry over the origin. Okay, that graph has symmetry over the origin. So that means that like this point, for example, and this point are direct reflections, are reflections of one another over that origin point. What's going on here, because of the symmetry, and because we're going out the same distance to the left and the same distance to the right, the area that we're capturing beneath the x-axis here is exactly equal in value to the area we're capturing above the x-axis over here, which means that the negative part and the positive part completely cancel one another out and give us a definite integral equal to 0. So that one was pretty easy too. You just had to draw a picture, think about it, and figure out that that's got to be equal to 0. And by the way, if you actually get in here and do this problem with the limit of a Riemann sum, you can, and it'll be long and kind of annoyingly hard, but it'll all come out to 0 in the end, which really demonstrates the power of thinking geometrically and doing this kind of reasoning. It saves you a ton of time. Now, I'm going to pause here for a moment to say that we're talking about two big strategies here. One is the limit of the Riemann sum, and the other is applying the basic properties and using geometry. In the next section, in 5.4, when we learn the fundamental theorem of calculus, that's when we're going to learn our main strategy for solving definite integrals. That's right. Neither of the two strategies I'm talking about in this section are neither of these are our main strategy. These are the definition strategy using the limit, and then the the sort of like the special tricks that work in certain specific situations. But we're going to learn soon how this all relates to antiderivatives, and then we're going to use antiderivatives to evaluate definite integrals in the future pretty much all the time. or most of the time. That'll be our primary tool, but we haven't gotten to that yet. So just hold your horses. We'll get there soon enough, and then you will have some really good foundational tools to do definite integrals in the future.